Hello and welcome to the Midterm 1 review session. My plan is to just go through one or both of the practice midterms that are available on Canvas, and then I'm happy to talk about anything at all that you want to. If you have any questions, you can send me a message in the chat, or you can send me an email. I will also keep my eye on my email. So let's go ahead and get started. Alright, so this is the Spring 2023 midterm. The first question here is a definite integral. Right away I notice we have an x squared and we have an x. X is almost the derivative of x squared. The derivative of x squared would be 2x, so I'm just missing that constant multiple of 2, but that constant multiple is not an issue. Whenever I see a function and its derivative, that's a good indication that u substitution is going to be the way to go. So I'm going to set u equal to x squared, and then du is 2x dx. And again, I don't actually have 2x, but that's fine. I can throw a 2 in there as long as I also put in a 1/2 to cancel out the 2. So I have this e to the x squared, which is e to the u. And then I have my 2x dx, which is du. And a very common mistake here would be to leave those bounds as 0 and 2. But when x is 0, well, u is still 0. But when x is 2, u is 2 squared, which is 4. When I have a definite integral and I do u substitution, I need to convert the bounds. And now I just need to find an antiderivative for e to the u, which is very simple. It's e to the u. I evaluate this at 4 and 0. And I'm done. That is option D if you distribute the 1/2 to the e to the 4th and the 1. Thank you, Gench and Bapanada Inc. for the support. I'm glad that you're here. Let's move on to question number 2. We're going to select the appropriate trig substitution. I see an x squared plus 7. And when I see something of the form x squared plus a squared, I'm going to substitute x equals tangent theta. I guess you could also do cotangent theta. That would be unusual, but it would work just fine. If we saw an x squared minus a squared, I would use x equals secant theta or cosecant theta. And lastly, if I see a squared minus x squared, I'm going to try substituting x equals either sine theta or cosine theta. So I don't see something squared here, but what is 7 the square of? It's the square root of 7. So I should try oh, sorry. I didn't write the a's in here. All of these have an a in them. So it's option C. I'm using tangent, and then the constant multiple is not just the 7, but it's the square root of that 7. So why don't we actually try to do this integral? So I'm going to make the substitution x equals root 7 tangent of theta. I didn't work this out beforehand, so hopefully it's not too bad. I'm also going to need to know what dx is. The derivative of tangent theta is secant squared d theta. So my integral is going to become 7 tangent squared of theta, that's x squared, I just squared this thing, over the square root of, again, x squared, which is 7 tangent squared theta plus 7. And then I have a dx, which we said is root 7 secant squared theta, d theta. And now the point of using this trig substitution is this is supposed to simplify using one of our favorite trig identities. In case you forget exactly what the trig identity is, let me remind you how to come up with it again, assuming that you remember at least that sine squared theta plus cosine squared theta equals 1. If I divide both sides here by cosine squared theta, and I'm doing that because I want to end up with a tangent squared, so I see a sine here, divide that by cosine to get tangent. This gives me tangent squared theta plus, and then cosine squared theta over cosine squared theta is 1, and the reciprocal of cosine squared theta is secant squared theta. So that's going to help us out here. Inside the square root, I can factor out a 7, which leaves me with tangent squared theta plus 1. And I'm going to rewrite that as secant squared theta and if I simplify that denominator, the square root of 7 secant squared theta is root 7 times secant theta, and now some cancellation happens. The root 7's cancel, that secant theta here cancels with one of these secant thetas, so I should be left with 7 tangent squared theta times secant theta d theta. Can we split screen when the Super Bowl starts? You're welcome to put up the Super Bowl on the other half of your screen. I think I would get in trouble if I tried to broadcast the Super Bowl on Twitch. Also, if you're looking for things to watch at the same time, because I'm a little boring, the Speed Chess Championship right now should be just finishing up. Maybe it just finished up. There were only several minutes left before the stream started. It's probably over now. You can go back and rewatch it later, I guess. Okay, I'm stalling because I'm trying to remember how to integrate tangent squared secant theta. Oh, this is awful, isn't it? I think this one's real bad. Hi Amelia, welcome to the stream. So the reason I think this is going to be terrible is my gut feeling is that I should try rewriting tangent squared theta as secant squared theta minus 1, but then I end up having to integrate secant cubed theta minus. Oh, no, wait. Maybe this isn't so bad. I thought I was going to have to integrate secant and secant cubed, but that's actually secant to the fourth and secant squared. Maybe this isn't so bad. In this problem, oh yeah, we don't need to we don't need to finish this off. I just thought, you know what, I'm going to go above and beyond for you all. I'm going to try to actually do this integral for you, because maybe it'll involve some concepts that you will need to use on the actual midterm. For the love of the game, exactly. Okay, so this is definitely something we can integrate, but I think with the secant to the fourth, we're going to end up converting that back, so I feel like I'm not going about this the most efficient way. You're getting to see my actual thought process here, because I haven't worked this out beforehand. Just some entertainment. Well, yeah, and not just entertainment, but, you know, we're reviewing some other things that might show up on the exam. If I wanted to do a u substitution where I set u equal to secant, then du would be secant tangent, but I'm not left with a secant tangent. If I tried to set u equal to tangent, then I would need a secant squared, which I don't have. Oh, no, it is terrible. I just added in an extra squared for no reason. So you do end up having to integrate secant cubed minus secant. So I think it actually is terrible. All right, let's move on. Okay, partial fractions. In the denominator, we have a linear term, we have a quadratic term, which is not reducible, it's not factorable, and then we have a quadratic term, which is a linear term squared. So when I have an x minus 3 squared in the denominator, I'm going to want something over x minus 3 and something over x minus 3 squared. I'm going to want one of those. Yeah, both of these terms. So it's going to be either C or D. In both of them, I have a constant over 2x plus 1, as I would expect. The difference is this x squared plus 1 term. When you have a quadratic in the denominator, we do actually need a cx plus d. So it's going to be option D. All right, x cubed e to the x. So yeah, my thought process here is I'd maybe hope to just recognize this as an antiderivative of something. It looks a little too complicated. Then I'd maybe like to use u sub because it's the simplest of the techniques that we have. I don't see a function and its derivative anywhere here. So probably integration by parts is going to be the way to go. Also, they gave us a hint. Well, they gave us some helpful information. The integral of x squared e to the x. That suggests to me that I should use integration by parts, because if I differentiate the x cubed, I'll get an x squared. Well, I guess actually a 3x squared, and they even helpfully put that 3 in there for us. And if I integrate e to the x, it's still e to the x. So let's try integration by parts. I'm going to set u equal to x cubed and dv equal to e to the x dx. That makes v e to the x, and du is 3x squared. So the integral is, let's see, the x cubed becomes u. Oh, sorry. I have to use the integration by parts formula, which let me remind you, is that the integral of u dv equals uv minus the integral of v du. So right here I have u dv. So this is going to be uv, which is x cubed e to the x, and that's going to get evaluated from 0 to 1, minus the integral from 0 to 1 of v du. And notice that this is exactly that. X squared e to the x and a 3. X squared e to the x and a 3. So I'm going to plug in 1. I'll get 1 cubed times e to the 1. I'll plug in 0. I'll get 0 cubed times e to the 0. And this quantity is 3e minus 6. I just need to be careful. That whole thing is subtracted, so I want to make sure the entire 3e minus 6 gets subtracted. That is, I want to put parentheses in. So this is e minus 0 minus 3e plus 6, which is minus 2e plus 6, or 6 minus 2e. All right. And once again, if you have questions at any point, send me a message in the chat or send me an email. Okay, so we've got our two functions. They're continuous. F is greater than g for all x greater than 1. That's what I see in the graph. F of x is greater than g of x once we get past x equals 1. And I know that the integral of g diverges. The integral from 1 to infinity of g of x diverges. So if I were to try to integrate f from 1 to infinity, well, because f is greater than g, the integral of f is going to be greater than the integral of g. And the fact that this integral diverges essentially means there's infinite area underneath g, and there's, as you can see from the picture, there's even more area underneath f. So the integral from 1 to infinity of f diverges. Okay, formula for integration by parts, we already wrote this, but let's write it again. uv minus the integral of v du. And probably this is a suggestion that we should use integration by parts here. I think that's a great idea. So we're going to split this up into the x to the 4th and the ln of x. I think I definitely want to differentiate the ln of x, because then it becomes 1 over x, which is a rational function, whereas the antiderivative of ln of x, I don't even remember it exactly off the top of my head. Supersum 177 to confirm for 5, if f of x diverges, then g of x could be either. If f were to diverge, then that's right. We wouldn't know anything about whether g converges or diverges. Yep, if you're bigger than a thing that diverges, you also diverge. If you're smaller than a thing that converges, you also converge. But here we wouldn't be able to say anything. Okay. So I want to differentiate the ln of x. I'm going to set that equal to u, and my dv then will be x to the 4th dx. So du is 1 over x dx. And I'm making sure to write the dx here. This is one of the most common mistakes I see, is just like writing du equals 1 over x. And then v would be 1/5 x to the 5th. So the integral of x to the fourth ln of x is uv, which is ln of x times 1/5 x to the fifth, and that gets evaluated from 1 to e, minus the integral from 1 to e of v to u, which is 1/5 x to the fifth times 1 over x dx. Alright, I should plug in e, and then plug in 1 and subtract those. And then let's simplify this. I'm going to pull the 1/5 outside, and that leaves me with x to the fifth divided by x, which is x to the fourth dx, and that's just a polynomial. It's just a power function, so I'm going to be able to integrate that pretty easily. Let's also start cleaning this up. The ln of e is 1, and the ln of 1 is 0. And once again, we need to anti-differentiate x to the fourth. That gives me 1/5 x to the fifth. It gets evaluated from 1 to e. Here I have 1/5 e to the fifth minus 0, and then minus 1/25. I'm just pulling that 1/5 outside and grouping it together with the other 1/5. And then I plug in e right here. I plug in 1. And I get this. Minus minus is plus. And if I really want to simplify this, this is 5/25 minus 1/25, which is 4/25 e to the fifth plus 1. Okay. I'm just going to double check my answer just to be sure. There are many steps here, and every once in a while I make a mistake. Four 25ths e to the fifth plus 1/25. Oh, okay. I made one small mistake at the end, which was I didn't distribute the 1/25 to that constant term. There we go. All right. Determine if the integral converges or diverges. And if it converges, we'll actually evaluate it. This is an improper integral because we have a bound of infinity. And what that really means is it's the limit as b approaches infinity of the integral from 1 to b, or from 0 to b, of e to the 2x. 1 over e to the 2x. The way that I'm going to integrate this is to rewrite that as e to the minus 2x. And if I wanted, I could use a u substitution. I could set u equal to minus 2x. But I've done enough of these integrals that I recognize the antiderivative here as minus 1/2 e to the minus 2x. The point is that if I differentiate this, the chain rule is going to give me an extra minus 2, which is going to cancel out the minus 1/2. That gets evaluated from 0 to b. So I have minus 1/2 e to the minus 2b minus 1/2 e to the minus 2 times 0. I get the limit of minus 1/2 e to the minus 2b plus 1/2. Well, e to the 0 is 1, so it's just plus 1/2. And, okay, so the b is going to infinity. What happens when you plug in a very large value of b? You multiply it by -2, so now it's a really big negative number, and e to a really big negative number is very close to 0. So this first term is approaching 0, which means overall the limit is 1/2, which means the integral converges. And it is equal to 1/2. All right. Another indefinite integral. This looks like an integration by parts. Partial fractions. So this should be equal to something of the form a over x plus b over x minus 1 plus c over x minus 1 squared. Let's see, a couple of questions here. If it diverges, then you would get infinity. Yeah, if you get infinity, or if somehow you get the limit not existing. Yeah, if the limit doesn't exist, then the integral diverges. Since the function is strictly positive, it's either going to converge or diverge to infinity. But yeah, getting infinity would be the typical way you would see an integral not convergent. And then is it possible to use the comparison theorem on question 7? What would you want to compare it to? So I guess one thing we could say is that 1 over e to the 2x is less than e to the minus x. Not for all values of x, but as long as x is at least, I think anytime x is positive. Yeah. So you could compare it to 1 over e to the x, or e to the minus x. You would then have to know that the integral of this thing converges. And even if you did that, it wouldn't help you find the actual value. So it's a nice idea using the comparison theorem here, but you are going to have to do all of this work anyway to find the value that it converges to. Let's see. Wouldn't be cx plus d over x minus 1 squared. So you absolutely could do that instead. You could go bx plus c over x minus 1 squared. That would also be perfectly acceptable. The only issue with that is just this is going to be a little bit harder to integrate. Right, like the integral of this thing is going to be b times the ln of the absolute value of x minus 1. The integral of this thing is going to be minus c over x minus 1. This would work just as well. It's just a little bit harder to actually integrate this. The reason that you do the bx plus c sometimes is if you cannot factor the numerator. You prefer to do this because it's easier to integrate. You just can't do that. You can't do this if the denominator doesn't factor. Okay, great question. So I want to find the values of a, b, and c. Plugging in x equals 1 looks like, sorry, I need to clear the denominators first. So I need to multiply everything by x times x minus 1 squared, which is going to give me a times x minus 1 squared plus b times x minus 1 plus c times x. And now I'm going to plug in x equals 1, which is going to give me, nope, that's c equals 1. That was easy. I'm also going to plug in x equals 0, and that's going to give me 1 equals a plus, oh, that's it. Okay, how do I find b? I think now I can just plug in any number other than 0 or 1. I guess I'll plug in 2. It'll tell me that 1 is equal to, let's see, if I plug in 2, I just get 1 squared, which is 1. So I get a plus 2b, because that's b times 2 times 1. And then I get 2c here. But I already know the values of a and c. So 2b is equal to negative 2, which means b is equal to negative 1. And there we go. We have decomposed this fraction. So let's just do the integral. We are rewriting the integrand as a over x, meaning 1 over x, plus b, which was minus 1, over x minus 1, plus c over x minus 1 squared, and c was also 1. So that's ln of the absolute value of x, don't forget those absolute value signs, minus ln of the absolute value of x minus 1, minus 1 over x minus 1, plus c. So you find a, b, and c by setting the equation from earlier to the numerator and solve as if they were variables. Yeah, so I took this equation and then I multiplied both sides by x times x minus 1 squared, which was just what I needed to multiply to get rid of all the fractions. And then I'm solving for these variables. The key observation is that for these expressions to be equal, they have to be equal no matter what value of x you plug in. And there are some really convenient values of x, like 1 and 0, because they make some of these things equal to 0. But I have 3 variables, so I need 3 equations. You can, I think almost always, probably actually always, you can plug in any 3 values and you'll get 3 equations that don't have x's in them. It'll just be a system of 3 equations with 3 variables, a, b, and c, and then you solve. But of course, yeah, plug in things that make some of these 0. It makes the equations that you have to solve pretty easy. All right. I'm going to double check this one too. One over x minus 1 minus log x minus 1 plus log x. Yep, we got it. Okay, indefinite integral. This is going to be a trig sub. the square root of x squared minus 4 just screams trig substitution. We've already talked about what substitutions to use. When we had x squared minus something squared, we were going to use secant. Alright, so I'm going to let x equal 2 secant theta. 2 because 2 squared is 4. So dx is 2 secant theta times tangent theta, d theta. And now let's make the substitution. X squared will be 4 secant squared theta. And then I have the square root of 4 secant squared theta minus 4 times dx. And a common mistake that I see here, or that I saw the last time I taught Calc 2, was not actually substituting the dx correctly. Like, I would just see the dx turn into a d theta. You actually have to differentiate to figure out how to substitute the dx. In this case, we get 2 secant theta tangent theta d theta. And this looks horrible, but the point of this substitution is a whole bunch of stuff is going to cancel out. And it's going to happen again with this trig identity that we discussed earlier. Tangent squared theta plus 1 equals secant squared theta. If I rearrange this, secant squared theta minus 1 is equal to tangent squared theta. And we're going to get a secant squared theta minus 1. In particular, we'll get that by factoring out a 4. There's a lot of writing here, but I'm making sure to carefully copy everything every time so that I don't make any mistakes. Oops, that's a 4, not a 2. I'm anticipating what's going to happen when I take the square root, but the secant squared theta minus 1 is tangent squared theta. And when I square root 4 tangent squared theta, I get 2 tangent theta. And now we finally get to cancel things out. I've got a 2 and a 2, a tangent theta and a tangent theta, and then the secant theta gets to cancel one of the secant thetas. So integral sign, that's important. So I'm left with 1 over 4 secant of theta. That's it. Wow. That's why we do the trig substitution. It makes it easy. And you might be thinking, how do I integrate 1 over secant of theta? But well, let me pull the 1/4 outside. The reciprocal of secant theta is cosine theta. So again, there was a lot of work to do to simplify this, but the point of the substitution is it turned this complicated thing into cosine of theta. All I have to actually integrate is cosine. So that gives me 1/4 sine of theta plus c. And let's just, okay. This is a little annoying. We have to evaluate sine of theta to convert this back to something in terms of x. But we had x equals 2 secant theta, which means that secant theta is x over 2. So let me draw a right triangle. Secant is the reciprocal of cosine. So if secant theta is x over 2, cosine theta is 2 over x. If I want to draw a triangle that has such an angle theta, the cosine is the adjacent over hypotenuse, so 2 over x would be the cosine of this angle. By the Pythagorean theorem, the other side is the square root of x squared minus 4, which of course it is. It's not a coincidence that that's the same quantity that's in the original integral. And then I need to know what sine of theta is. It's opposite over hypotenuse. So root x squared minus 4 over x. And that is the integral. I'm definitely double checking this one. Yep. Alright. Is this the last problem? This is the last problem on the Spring 2023 Midterm 1. Integral of secant to the 4th x. Oh, yeah, we almost did this one earlier, back when I made the mistake on that, it was the one where we had to identify the trig sub, but not actually carry it out. So, secant to the 4th, I'm going to use this trig identity again. I'll copy it here for convenient reference. And the point is, I'm not going to convert all of the secants using this formula. I'm just going to split up secant to the 4th into secant squared, and I'm only going to replace one of them. So secant squared is equal to tangent squared theta plus 1. Will the same number of questions be on the exam tomorrow? I am not sure. I'm not teaching Calc 2 this semester, so I'm not up to date with all of the details about the course, but I'm just checking the announcement in Canvas to see if I can answer your question. The announcement does not specify the number of questions, so I'm not sure. It wouldn't be terribly different, I have to imagine. They try to write exams which are a reasonable length. This is a good point that Hazard brings up, which is that the material was rearranged a little bit. So you won't see exactly the same topics. And yeah, so it surely will not be exactly the same number of questions, but this should give you a rough idea of what the length will be. Okay, so I've got my two terms. Now I know how to integrate secant squared because I just recognize that as the derivative of tangent. So I'm going to just split this up into two integrals. And then we can think about how to integrate this. But when I integrate secants and tangents, I'm usually looking for a u sub, and I see, I see a function which is tangent. That thing is getting squared, but there's a tangent there. And then I see its derivative, which is secant squared. So I'm going to try u equals tangent x, which means du is secant squared x dx. So I have u squared, that's this part, and then the secant squared x dx is du. And let's just go ahead and write that as tangent x plus c. The integral of u squared du is 1/3 u cubed. And if we substitute tangent x back in, this is tangent cubed x. There we go. One practice exam done. Questions about anything from this practice exam? And what do you want me to do next? Do folks want to see the other practice midterm, the one from fall 2022? Or do you want to talk about any of these specific topics in more detail? I've got a textbook here. I can pull up some examples of any topic you want to talk about. Trig sub, integration by parts, u sub, partial fractions, trig integrals that don't involve trig substitution. What other topics are there? We did an improper integral. We could do more of those. New this semester, I believe. I guess I don't know if the changes were this semester or if it happened last semester. Anyway, new since the last new since spring 2023 at least. Separable differential equations and initial value problems, area between curves, volumes with cross sections. What do you all want me to talk about? Okay, Hazard says, can you go over volumes by known cross sections or areas between curves? PRX DGYY agrees. Okay, we can do those. Jude, if you have the chance, can you show how to integrate x squared square root of 9 minus x squared? Okay, let me do that one first. If anyone has any particular problems about volumes or areas between curves, that's helpful. If not, I can pull up some examples. So let me integrate x squared times the square root of 9 minus x squared. Okay. Again, we've already discussed the general rules for which trig substitutions are helpful. In this case, it's going to be x. X equals 3 sine theta. So dx is going to be 3 cosine theta d theta. And I'm going to get 9 sine squared theta times the square root of 9 minus 9 sine squared theta times dx, which is 3 cosine theta d theta. When I factor out that 9, I get 1 minus sine squared theta, which is cosine squared theta. And we're about to find out how difficult of a problem Jude has given me to try here. We're going to end up with powers of sines and cosines, and it all depends on if the powers are both even, it's going to be annoying. If one of the powers at least is odd, it won't be too bad. The square root is just 3 cosine of theta. Oh, no, this isn't going to be nice, is it? Well, it'll just be a good excuse, an opportunity for me to remind you how to integrate using some trig identities. So if I collect all the constants together, I get 81 sine squared theta times cosine squared theta. Okay, so when both of the powers are even, I'm going to need to use one of the double angle formulas. Which I believe, now I haven't thought about these trig identities in about 2 years, so correct me if I'm wrong, but I believe cosine squared theta is equal to 1 plus cosine 2 theta over 2, and sine squared theta is 1 minus cosine of 2 theta over 2. Again, someone please fact check me, because I haven't thought about this in I think 2 years. Would you get a problem that doesn't simplify nicely like this on an exam? I can't know for sure. I suspect this is on the, in theory this is fair game, but it is definitely, it's a hard problem. It involves a lot of different things, like, applying a trig substitution and then doing a pretty annoying trig integral. I would hope that you wouldn't get a problem. I would hope that you wouldn't have to do so much in one problem, but I don't know for sure, because I'm not involved with the teaching of Math 2300 this semester. If I were writing the exam, and this is just my personal opinion, I would make this like an x cubed, so that you still have to end up doing this trig integral, but at least with an odd power, there's still work to do for sure. But it's not quite as bad. But it's a very long-winded way to say I don't know. So I'm trying to decide which of these two trig identities to use. I like that this one doesn't have any negative signs. But do I want to only have cosines involved? I kind of actually like having a mix of sines and cosines because it opens up opportunities for U substitution. Oh well, Jude, this is a really good problem, and even if you don't end up seeing a single problem this long on the exam, many different parts of this problem definitely could. I think this is a fantastic problem to work through because it, like maybe just this integral by itself could show up. So I think it's great for us to review how to integrate a product of sines and cosines with even powers. I think it's actually at the end of the day not going to matter too much which I do. So let me just pick one. Let's do this one. So I have my sine squared theta, and then my cosine squared I'm going to replace with 1 plus cosine of 2 theta over 2. I'm debating whether I've actually gone about this in the most efficient way. I don't think there's a better way. Maybe there is, though. This is annoying. I have to integrate sine squared, and I have to integrate sine squared cosine of 2 theta. Yeah, okay, I think actually we should... I think we should replace both of these. Okay, so if I pull out the 81/4, I'm left with 1 minus cosine 2 theta times 1 plus cosine of 2 theta. And this is nice because it actually, when I FOIL this out, stuff cancels. So I'm left with 1 minus cosine squared of 2 theta. And 1 minus cosine is sine squared. And then I'm going to use this identity once more. So I do suspect that I actually have not taken the most direct route, but we are making progress. See, now I have no powers of trig functions. I just have a cosine and a constant term that I need to integrate. So I'll split this into 2 integrals. The 1/2 and then the cosine of 2 theta. Notice the 2 in the denominator, I pulled that outside and combined it with the 4. And we have a minus sign. So I think I've done this all correctly. This is going to be 81/8 times theta. That's it. And this will become 81/16 sine of 2 theta. When you integrate cosine theta, you get sine of 2 theta, and you also get a 1/2. Okay, so we need to get this back in terms of x. X was 3 sine theta, which means x over 3 is equal to sine theta, which means theta is arcsine of x over 3. So I've got 81/8 arcsine of x over 3 minus 81. Okay, I need to know what sine of 2 theta is. This is a fantastic problem. Again, yeah, I am now convinced that this is too hard of a problem. But again, this could be like 2 or 3 different problems put together, which you might actually see on the exam. So it's all good stuff to review. Double angle combo identity. Yeah, I need to. Yeah. Okay. So I need to know what sine of 2 theta is. So sine of 2 theta, I have an identity, which is sine of 2 theta is equal to 2 sine theta cosine theta. I'm going to use that. And I know what sine theta is. I just need to figure out what cosine theta is. But cosine theta is the square root of 1 minus sine squared theta. Okay, so here we go. So sine 2 theta, first of all, I'm going to rewrite that as 2 sine theta cosine theta. Okay, so 2/16 is 1/8. And then sine theta is x over 3. And then cosine theta is the square root of 1 minus sine squared theta. Sine squared theta is x squared over 9. So we're done here. Oop, plus c. We are done here. I'm going to simplify this just a little bit to make it easier when I double check my work. 81/8, and I have an x. I'm going to take this 3 and shove it inside the square root. Inside the square root, it'll become a 9, so I'll get 9 minus x squared. Alright, so here's my answer. We were trying to integrate x squared times the square root of 9 minus x squared. Was that the original integral? Yep. Wolfram alpha tells me, oh geez. Wolfram alpha gives me a different answer, but that doesn't mean this is wrong, because a lot of times you can write things in different ways. I'm going to differentiate my answer and see if I get the thing that I started out with. And by I mean Wolfram alpha. Okay, I do appear to have made a mistake somewhere. But, you know, this is a good demonstration of many of the techniques that you could use to integrate. You know, I could go back and try to find my mistake, but it probably would not be worth our time. Okay, Salacious Bikram says sine squared theta cosine squared theta is 1/4 sine squared of 2 theta. Yeah. So that you're basically squaring this identity right here. Yeah. So that would have been a more direct way to simplify from here. And that, oh, we did end up with that. We ended up with the 1/4 sine squared of 2 theta. Which is, that's what you said, right? Yep. So it looks like we're good up to here. Oh, here's my mistake. That should have been a 4 theta. Because we already had 2 theta, and when we use that identity, it gets doubled. Okay. So that should be a 4 theta, and then we're actually dividing by 4, so it becomes 32, and I don't want to deal with that. I mean, it's definitely doable, but it'd be a pain. Okay, so let's do some areas between curves and volumes with cross sections, and then also separable equations. Yeah. If anyone has sample questions related to these topics that you'd like to see, feel free to let me know. Otherwise, I'm just gonna take a minute and find some problems. I guess, can anyone tell me with like areas between curves, what kind of, like, how complicated did it get? in Calc 2, were you all integrating ever with respect to y instead of x? Do you want to see something like that? Or yeah, I guess that's my question, is how complicated do you want to see the example? For how complicated of an example do you want to see for areas between curves? Okay, so let me do a volume with cross sections, and then we can come back to areas between curves. It'd be great if someone could let me know, whoever requested it, if you could let me know if you have a recommendation for how complicated you would like it to be. I guess I can also try to find in the sample midterms, maybe one of them has a problem with areas between curves. I'm surprised they don't. All right. Well, here's a problem. We're gonna let the base of a solid be the first quadrant region bounded by y equals 1 minus x squared over 4, the x-axis, and the y-axis. And we'll suppose that cross sections perpendicular to the x-axis are squares. And we're going to find the volume. Okay, so the first thing that I do is I draw the region. One minus x squared over 4. That is the parabola that opens downward. Has a y-intercept of 1. The x-intercepts are going to be 2 and negative 2. And I would find that by setting 1 minus x squared over 4 equal to 0. It's going to look something like this. So here's my region. And then I'm also going to try to draw a 3D picture, because it's going to help me figure out how to set up the integral. This is not a necessary step. It helps me at least. So I'm gonna sketch this region of the plane. So there's the region. And then they're telling me about cross sections perpendicular to the x-axis. Perpendicular to the x-axis is going to mean slicing it this way. And these cross sections are going to be squares. Okay, so at each x value, I get a different cross section. So I'm integrating with respect to x. And I'm integrating from 0 to 2. And then if I look at a slice, that's some x value, what's the volume of that slice? Let's say rectangular prism. The thickness, if I draw the full prism here to make it look 3D, the thickness is dx, and I've already got the dx there. And then this side is, well, it's given by the equation of the parabola, so it's 1 minus x squared over 2, sorry, x squared over 4. That's this side, but the cross section is a square, so the other side is the same. So I end up integrating 1 minus x squared over 4 squared times dx. And this is not too bad of an integral. When I square this out, I'm going to get 1 minus, minus x squared over 2 plus x to the 4th over 16. So I'll find an antiderivative, which is x minus x cubed over 6 plus x to the 5th over 80. I evaluate from 0 to 2. If I plug in 0, I do get 0. Okay, and I'm just double checking here. This is correct. I'm not going to bother simplifying that fraction. Brian likes math. Hello, welcome. So that's a problem with cross sections. Questions about cross sections? And Jude and Brian likes math, thank you for following. Questions from anyone about cross sections before we do a problem with areas between curves? I'm doing great today, Brian. I'm getting to tell you about some cool math. Do some integrals. It's a beautiful day outside. What more could you want? How are you doing today, Brian? Problem about an axis that's not y and x. Oh. Okay. I suppose we could do something like that. Trying to see if the book I have here has any problems where if I just need to change one of them. Ooh, this one looks promising. No, that's perpendicular to the x-axis. I want perpendicular to the z-axis. Maybe that's what I want. Oh, wait, like x equals 8. Well, if it's perpendicular to x equals 8, that's the same thing as being perpendicular to the y-axis. Or sorry, it's perpendicular to the x-axis. Yeah, there are a lot of little details with these problems. If you have a problem for me with a different axis, I'd be happy to do it. It doesn't change that much. I am curious, like what sorts of problems with volumes have been on midterms in the past. Usually this would be midterm, or I guess in the past, what I mean is that these have, in the past, have been midterm 2 problems. So, yeah, well, this is a solid of revolution. Maybe fall 2022 had cross sections. Okay, maybe let me... Oh, we have a suggestion. X equals 8, y squared, x equals 8, about... Oh, well that's a solid of revolution. I see what you mean, but those aren't on this exam, right? I want to double check so I don't tell you something false about what's going to be on the exam. Yeah, midterm 1 is only covering volumes with cross sections. Midterm 2 has solids of revolution. That's at least what I'm seeing on the Canvas page. If anyone knows otherwise, please let me know. But on the Canvas page about the exams, I'm just seeing that midterm 2 has solids of revolution. Okay, but we may as well work through one more example with a volume with cross sections. So this is the fall 2022 midterm 2. Okay, so a solid has its base lying in the xy plane, in the region bounded by the curve y equals 1 minus x, the x-axis and the y-axis. This one is... It's fairly similar to the one we just did, but it's actually a little bit simpler because the region is bounded by a line. Y equals 1 minus x looks like this. It goes through 0, 1, and 1, 0. So the region is just a triangle. Cross sections perpendicular to the x-axis or squares. Okay. Okay, cross section's perpendicular to the x-axis, so it's going to slice this way. And if we draw one of those typical cross sections, it's going to be a square. And once again, if I give it a little bit of thickness, so we can see what it looks like in 3D. We're integrating with respect to x, and in fact the dx is the thickness of that slab. We're going from 0 to 1, and this is 1 minus x. It's just coming from the equation we were given. And that is also 1 minus x. So 1 minus x squared. Wait, nope. The integral of 2x is just x squared. And then I get 1/3 x cubed I'm just getting 1/3. Yeah, I think that's right. Let's see. Yeah, so volumes with cross sections are in the exam. They were not in the past, which is why I'm looking at a midterm 2 right now. But they will be on this exam. Volumes of solids of revolution will not be. Okay, but areas between curves could also be on the exam, and that was requested, but I have not yet done an example. So I'm just going to pick one from my book here that looks fun. Can I do another one? I'd be happy to do another one. If you have one picked out for me, that would be helpful. But I want to do areas between curves, and then we can come back to that. Okay, so let's find the area between, I'm just picking one from this book here. I don't know how interesting it'll end up being, but we will see. Area between y equals e to the x, y equals e to the minus x, x equals 0, and x equals 1. Okay. I always find it really helpful to draw a picture. So e to the x looks like this. It goes through 1, and e to the minus x looks like this. And then they also told us to just look at the area between x equals 0 and x equals 1. But this is a pretty straightforward problem. We're integrating from x equals 0 to x equals 1, and we do the equation of the top curve minus the equation of the bottom curve. So it'll be e to the x minus e to the minus x. And the reason for that is that if we were to split this up into a bunch of little rectangles, like let's say this happens at x, the width is going to be dx, and the height is e to the x minus e to the minus x. So we're doing width times height, which is the area of a rectangle, and then we're adding up all of those rectangles. So I would find an antiderivative, which ends up just being 2, oh no, sorry, that's not right. E to the x plus e to the minus x. Yep. So e to the 1 plus e to the minus 1 minus e to the 0 plus e to the minus 0. This is e plus 1 over e minus, well, this is going to be 1 plus 1, so it's minus 2. This New Rocha, yeah, this is a review session for Calc 2. I'm not, if you're not enrolled in our Calc 2 course here at CU Boulder, I'm curious how you came across the stream. But in any case, welcome. We're doing some Calc 2 stuff. I guess this topic here was introduced at the very end of Calc 1 last fall. There was just one day on the calendar, I believe. I have the calendar here. Yeah. Friday, December 5th, we covered this in Calc 1. I don't know how much time you saw on this topic in Calc 2. What do I think are the hardest topics for the test? That's a deeply personal question. It's I don't know. Like it just depends what you find challenging. For example, these volumes with cross sections, it can be hard to just think through the setup because it involves sort of thinking about something in 3 dimensions. But once we actually set up the integral, it was not too difficult to do. Whereas some integrals are maybe a little more, well, you don't have to, think about the geometry, but the actual computation, the calculation could get very, very intricate and detailed. So there are a lot of things that are difficult for different reasons. The best thing I think for you all to do as you're preparing for the exam is to work through one of the practice midterms. I guess we did the spring 2023, but work through the other one and identify the topics that cause you the most trouble. Okay, so we've done areas between curves. It gets more challenging than this. So let me, oh, here's a good one. So I want to do a harder areas between curves problem. Let's find the area between x equals y squared minus 2y and x minus y equals 4. This one will be fun. Okay, so let's start by sketching a graph. X minus y equals 4. I can rearrange that as y equals x minus 4. Which, oh, that's not quite right. I didn't know in advance where I needed to to draw the axes. But that's going to look something like this. And then x equals y squared minus 2y. I can factor as y times y minus 2. So this is a parabola that opens to the right. And it has y-intercepts at 0 and 2. Yeah, super someone, you are subtracting the equations and using the domain as bounds. Yeah, that's what's happening. You just, what can be a little tricky sometimes is figuring out what order to subtract them in. You want to do the top minus the bottom. It might take a little bit of thought sometimes if you're just given the equations to figure out which one's the top curve and which one's the bottom. One sort of practical way, well, you can always just like plug in an x value and see which expression is bigger. If you pick an order and you get a negative number at the end, well, this is positive, but if you were to get a negative number, that would tell you that either you made a mistake somewhere or possibly the mistake you made was subtracting the things in the wrong order. This problem here is going to be tricky because we're going to end up needing to integrate with respect to y instead of x. I don't know if that's a topic that was covered in Calc 2. I'm assuming it was, but I don't know for sure. But I'm going to set these equations equal to each other to find the places where these curves intersect. All right, so I have well, I'm trying to solve these equations here. I guess I could also write this as x equals y plus 4. If I add the y over, yeah, so x is y plus 4. And if x is equal to this, I can set these two things equal to each other. So y squared minus 2y is equal to y plus 4. Let me get this all on one side of the equation. Y squared minus 3y minus 4 equals 0. That will factor as y minus 4y plus 1. Yep. So y is 4 or negative 1. These are the y values. And the x values, when y is 4, x is, oh, x is always y plus 4. So it's going to be 4 plus 4, which is 8. And when y is negative 1, x is going to be, again, y plus 4. So negative 1 plus 4, which is 3. So what is all this telling us? It tells us that there's an intersection where x is 3 and y is negative 1. So let me plot the point 3, negative 1. And it tells us that there's an intersection at x equals 8 and y equals 4. Okay, so x equals 8 happens right here. I'm going to need to extend this line. And the point 8, 4 is right here. And we said this is a sideways opening parabola, so you can see it. It actually does go through those points. Now, what's challenging about this problem, again, is that, well, the easiest way is going to be to integrate with respect to y. If you want to integrate with respect to x, you can, but you need to split it into two regions. And to express this as a function of y, you're going to need to solve this equation for y, which is going to be a little bit challenging. But the easier way is to integrate with respect to x. Sorry, integrate with respect to y. And then our y values now, let me draw in the region. The y values go from negative 1 up to positive 4. So I'm going to integrate from negative 1 to 4. And I'm subtracting the x values. The point being that at any given y value, if I make a little slice, a little rectangle, the height of the rectangle is the dy. And then the width of the rectangle is this x value minus this x value. So it's the x value coming from the line, and that line was this equation. The x value is y plus 4. And then the x value from the parabola is y squared minus 2y. So this is the integral we would do. Should we expect these type of problems on the exam? Yeah, I know that areas between curves is a topic that will be covered on the exam. I don't know exactly what level of difficulty you should expect. I would go back and look at your WebAssign and see what kinds of problems you got on areas between curves. Integration with respect to y, I think it's a standard Calc 2 topic. I would think that this is fair game. But I would now simplify this, so I have minus y squared plus 3y, that's 1y minus minus, which is plus another 2y, plus 4. So you would get minus 1/3 y cubed plus 3/2 y squared plus 4y. You'd evaluate that from negative 1 to 4. That doesn't look like a lot of fun to do. But it is just arithmetic beyond this point. All right. Were there any other topics that... Oh, someone asked about separable equations. So let me do a problem like that. Let me see where in this book I can find some separable differential equations. Okay. Here's a good one. dy dx is minus y squared x times x squared plus 2 to the fourth. Oh, geez. Oh, okay, yeah. I thought this was going to be really bad, but it's not. And y equals 1 at x equals 0. Okay, so if dy dx is minus y squared x times x squared plus 2 to the fourth, separable means that I can separate the x's and y's. So I'm going to bring the y squared over by dividing both sides by y squared, and on the right side that leaves me with minus x times x squared plus 2 to the fourth, and I'm bringing the dx over. So basically I'm multiplying both sides by dx, and I'm dividing both sides by y squared. And then I'm going to integrate both sides of this equation. On the left, the integral of 1 over y squared is minus 1 over y. And then here, we're going to do a u sub. We're going to set u equal to x squared plus 2. So du is 2x dx. I don't quite have a 2x, but I can throw a 2 in as long as I also put in a 1/2. So I have u to the fourth, and then the 2x dx is du. This is going to become 1/5 u to the fifth plus c. So I get 1/10 u to the fifth, and u was x squared plus 2. So I have an equation, but it has this constant. I'm going to use my initial condition to find the value of the constant. So y equals 1 when x equals 0. That means minus 1 equals minus 1/10 times 2 plus c. So minus 1 equals minus 1/5 plus c. If I add 1/5 to both sides, I get minus 4/5 equals c. So my equation is minus 1 over y equals minus 1/10 times x squared plus 2 minus 4/5. I guess we could simplify this a little bit. I could multiply everything by -1 to get rid of all those negative signs. And then I suppose I could take the reciprocal to find the value of y. I forgot the 5th power. Oh, yeah. Oh no. Yeah, that should be a 5th power right there. So that should be 2 to the 5th. So this should be minus 32/10. Minus 32/10 is minus 16/5. So I add 16/5 to both sides, and I get c equals 11/5. Hopefully this is right now. Do I think points would be deducted if you don't simplify? My guess is no. I don't know for sure. I mean, you would get nearly all of the points, if not actually all of the points, if you don't simplify. Sometimes it's not possible to simplify and get it to y equals. It's nice to do this, but yeah, I don't know. Again, I'm speculating because I'm not involved in the writing or the grading of the exams for Calc 2. But yeah, it's really just separating x and y and then integrating both sides. That's what it is. Most differential equations are harder than this because you can't separate the x and y, but that is a topic for a different course. Okay, I think we've now discussed all of the topics that were requested. Does anyone have any last questions before we wrap up? Discrete lectures. Wait, are you in my discrete class? Oh, okay. And you're also in Calc 2? That's a good combo, good pair of classes. Yeah, glad to hear that you're enjoying discrete. I am too. We're going to do proofs by contradiction starting tomorrow, so that'll be fun. What about the integral of arcsine of x? Oh, that's a great one. That's a great one. I'm trying to think about whether you can do this with a u sub. Like if you set u equal, obviously setting u equal to x doesn't ever help. Well, what if you set u equal to sine inverse of x? I wonder if that would Probably that wouldn't work. What you can do is actually integration by parts, which is crazy. It seems crazy because there's only, you don't even have two things multiplied together to be the u and the du. But what you can do, and this is the same way you integrate ln of x, is you can write this as 1 times arc sine of x. Which, again, it seems like a silly thing to do, but it works. And am I going to differentiate or integrate the arc sine? Well, the whole point is that I don't know how to integrate arc sine. So I should set u equal to arc sine so that I end up differentiating it. And that'll give me 1 over root 1 minus x squared dx. And then that means the dv just has to be 1 times dx, or dx. So v is going to be equal to x. And then integration by parts says this is equal to uv, which would be x arc sine of x, minus the integral of v du, which is x over root 1 minus x squared. So we have to be able to integrate this. And it kind of looks like we've just made things worse, but actually this can be integrated with a substitution. I'm going to use w instead of v, or u, because I've already used u. So I'm going to set w equal to 1 minus x squared, which means dw is minus 2x dx. I'm going to bring this minus sign inside the integral. I'll rewrite that. I'll bring the minus sign inside the integral. And then I also wanted a 2, so let's throw in a 2, and then also a 1/2. And now we've got 1/2 times the integral of dw and 1 over root w. One over root w means w to the minus 1/2. And let's see, I add 1 and then I divide by, so I add 1 to the power, so it goes up to w to the 1/2, and then I divide by 1/2. And strangely enough, these 1/2s cancel out. I should also not forget the plus c. So I get x times arc sine of x plus w to the 1/2 plus c, and then let's just substitute back in w, which was 1 minus x squared, and if we want, we could rewrite that, the 1/2 power, as a square root. So there you go. It's a fairly standard integration by parts problem. Once you have this clever idea to throw in a 1 and make the 1 dx your dv. Yeah, the same trick works. I mean, it should work with any of the other inverse trig functions, but it also works with ln of x. This is one way to integrate ln of x. Any other questions? Alright, well, we just hit the 2-hour mark, so I think this would be a good time to call it a day. Thanks for joining. If you missed any of the stream, if you joined partway through, the recording will be available on Twitch afterward. I'll also put it up on YouTube. Best of luck with the exam tomorrow, and maybe I will see you in another stream in about a month from now, reviewing for the second midterm.